Greetings, everyone. So let's continue with the study of section 5.3. Part of the section is on indefinite integrals, which was mentioned in an earlier video, but I wanted to give some more practice with that concept. And so remember, for an indefinite integral, we're looking at an integral symbol where there are no upper or lower limits of integration. It's just it's said this way, the indefinite integral of f of x dx. And by this we mean we're trying to find the most general antiderivative of the function f of x. And so this is just going to be capital F of x, of course, plus a constant, where, and let me put this in smaller print here, where capital F prime is equal to lowercase f. Again, taking the derivative of capital F will give us lowercase f. Of course, derivative of c will be 0, so that goes away in the process. But the point is, with this collection of symbols in green here, we're trying to find the most general antiderivative. Let's get some examples in. So at this point of our development of taking antiderivatives, like back in section 4.8, we were trying to just recognize the integrand as the derivative of some known function, or we're reversing the power rule, or I guess there's one more at this point. There's some algebra we could do to rewrite it and then do one of the two things just described. And so in this example here, hopefully you already know what the answer is. You can already recognize it, because this is one of those examples where we should just look at the integrand here and say, I know what function I could take the derivative of to get secant of x times tangent of x. And then we should know the answer to this. We should know that the derivative of secant x is secant x tangent x. So this answer to this indefinite integral, or the most general antiderivative of secant x tangent x with respect to x, is secant of x plus a constant. All right, here's the next one. Pause the video and go ahead and give this one a try. Hopefully you're back from your work and you've done it successfully. Here, we're algebraically just going to go term by term and reverse the power rule. And so t to the fourth, when I take its antiderivative, add 1 to the 4 to get 5, divide by that 5. The 5s are going to cancel. We're going to get t to the fifth. Similarly here, minus t cubed, when I take the 2 and the exponent of this second term and add 1 to it to get 3, divide by 3, I get this expression here, and then plus 7t. Of course, I'm not done yet. I need to add my constant of integration, and so we get this. Now remember, for taking an antiderivative, to see if you've done it well, you can just take the derivative of the result and see if you get back to where you started. So one way to just check our work really quickly would be to differentiate with respect to t all of the stuff that we just had as the result. And when we do this, derivative of t to the fifth is going to be 5t to the fourth. Derivative of t cubed is going to be 3t squared, so minus 3t squared, plus 7. The derivative of a constant is 0. I get the same results here that I got, or that we had in the integrand here. And as long as those match, then I've done this process properly. So you can check your work. However, sometimes checking your work isn't always that efficient. No, efficient's not the right word. It's harder to see sometimes the checked work is the right answer. Because in this example here, you need to do some algebra first. So pause the video, do some algebra first before doing any calculus, and then we'll see if you did it right. All right, so hopefully you're able to get some algebra done here. And what do we get? So when I square the v squared plus 2, all of this stuff here, we're going to get v to the fourth plus 4v squared plus 4. And then I'm going to have to multiply that by another v. So let's just write this all out. V to the fourth times v will be v to the fifth. The 4v squared times v will be 4v cubed, and then plus 4 times v, or 4v. If you need to go write out the algebra for that, go right ahead. I'm assuming that you can do that. If you need to send me a note saying I didn't get the algebra, then go ahead and send me a note and I'll go try to explain it to you, or come in and see me. So taking the antiderivative term by term, antiderivative of v to the fifth will be 1/6 v to the sixth. and then we're going to get a plus v to the fourth. When I divide by that new exponent, the fourths cancel, and then we're going to have a plus 2v squared, and then plus c. So hopefully that was the answer that you got. Here's the next one. Go ahead and give this one a try. Pause the video. Hopefully you're following my advice and doing some algebra first. What you cannot do here is you cannot take the antiderivative of the numerator and the antiderivative of the denominator and then divide the results. If you do that, your result will be incorrect, as we demonstrated in section 4.8 in some examples that we went through. But nonetheless, what we should do in our rewrite, or what we should end up with, is we just need to subtract the exponents. Remember, in the denominator here we have x to the 1/2 power. And so as I divide term by term, I'm just subtracting exponents. So we're going to end up with a 2x to the 3/2, okay, or 1 1/2, which is 3/2, minus 5x to the 1/2. 1 minus a half is a half. Plus 3, now there's an x to the 0 there, minus 1/2 will be x to the negative 1/2. All with respect to x. And now we can reverse the power rule. If you didn't get that step, but now you want to try reversing the power rule on your own, pause the video, go do that, and come back and see if you agree with me. All right, so when I add 1 to the 3/2 in that first term, then I'm going to get 5/2, and then I got to divide by 5/2, which is the same as multiplying by 2/5. So 2 times 2/5 will be 4/5. Times x to the 5/2, and then minus, when I add 1 to the 1/2 of this exponent, I get 3/2, and then I got to multiply by 2/3, divide by 3/2. So 2/3 times 5 will be 10/3, x to the 3/2. And then in the last one here, the negative 1/2, when I add 1 to that, we'll get a positive 1/2. Dividing by positive 1/2 is the same as multiplying by 2. So we're going to end up with 6x to the 1/2. And then, of course, plus c. Don't forget your plus c. There's our answer. How about one more? This is going to require you to use a little bit of trig knowledge to rewrite this first. So go ahead and pause the video, use a little trig, see if you can get this done. Now, hopefully, with some trig understanding, you were able to rewrite this, at least the denominator. We get sine of theta over cosine squared theta, and then we're still integrating with respect to theta. At this point, it might be still a little bit tricky to see. And this, hopefully you got it. But if you didn't, don't be too upset. You're going to get it every other time after this. Think about cosine squared theta as cosine theta times cosine theta in the denominator here, like this. And then I'm doing way too much rewrite here. You don't need to do this much rewrite, but I want you to see the logic for this. I want everybody to see the logic for this. All of these steps are algebraically equivalent. So I just separated the fractions here, and now in my rewrite, you can hopefully see that we get, sine of theta over cosine theta is going to be tangent theta. 1 over cosine is secant theta. And of course, we still have our d theta. I know the order is commuted, but that's okay. The multiplication commutes. And so this is the antiderivative, the most general antiderivative of secant theta times tangent theta, which we saw already earlier in this earlier example. It's antiderivative secant of theta. And don't forget your plus c. Hopefully that was enough practice to get you where you need to be as far as being able to handle the homework and any other problems you might see on an assessment. If you still need more practice, let me know. Send me a note, and I can make some more examples for you. Go study.